Okay, this is going to be lecture 3 for the Discrete Structures class. Now, I'm also teaching a class called Set Theory and Logic, and there is an awful lot of overlap in the material between the two classes. So sometimes for their class, I will show them a recording that I made for your class, and vice versa. It all depends upon which class covers that topic first. Today's lecture is going to be about set theory, and also will be the same situation for Wednesday's lecture. Okay, and I've already covered that last week with my set theory and logic class. So you're going to see in the recording at the top of the page it'll say set theory and logic, but don't panic, this is the correct lecture for discrete structures. This lecture number 3 is going to be comprised of 2 short lectures from the set theory and logic class. You don't have to watch 2 videos. I'm taking both of those and I'm editing them together, and I'm also going to cut out some of the material that you don't need for the discrete structures class. Enjoy. I'm going to write down a couple words here, which are set and element. You probably already have used these in the past, but that's okay if you haven't. Okay, a set is a collection of things. Okay. Or if you don't like the word things, if that sounds too juvenile, we could say it's a collection of items if you would rather have that. Okay, and the next important word is the items in the set are called elements of the set. So that's the basis. Those 2 words are the basis of set theory. There's 2 parts to this class. Not a part 1 and a part 2 really, but just two things that are melded together all the way through. We're going to do set theory and we're also going to do logic. Okay, and these 2 words are the basis of set theory, is the word set and the word element. Okay, all right, now, so a set is a collection of items. Most of the time in math, those items will be numbers, but they don't have to be. Okay, now, when we do a set, we use these curly brackets or braces or whatever you want to call them. That denotes a set. Okay? And we write the elements inside there. Usually, I'm going to show you other ways to do it as well, but for right now, I'm just going to write the set of the first 5 integers. If you don't know that word integer, I'll define that in a minute, but I'm just going to write the numbers 1, 2, 3, 4, 5 in this set. We separate them with commas. So, you know, this is kind of trivial, but it's very important, okay? Number 1, sets need to have curly brackets around them if you're going to write the set out. And number 2, the elements in the set need to be separated by commas. You don't have to write the whole set out. You can just give it a name instead. Okay, like, you know, the number pi, we can't write the whole number out, right? So what do? We give it a name. We call it pi. This is not a rule, but it is a custom that if you're going to give a set a name, most people use capital letters for the names of sets, and that's so that you don't get it confused with a variable. Usually we use lowercase letters for variables, uppercase letters for sets. Okay, so there I have a set that I've named A, and it has how many elements? 5 of them. Now, this is super important. The order that you write the elements does not matter. Okay, I can do this. I can say that A also equals this. That's the same set. Okay? I like to think of it like this. A set is a cardboard box. And the things that you see when you peer into the box are the elements. Okay? Now, if I had a cardboard box, and let's just pretend that there was 4 wooden blocks in there, and one block had a 1 on it, and another one had a 2, and a 3, and a 4, and a 5. Oh, I said 4 blocks, I meant 5 blocks. Okay? If I took that box and then shook it up, and then peered inside it again, I would probably see those 5 wooden blocks, in a different order, wouldn't I? But it's still the same box with the same things in it, correct? So that's why when you rearrange the order of the elements in a set, it does not actually change the set. Okay? Easy way to remember that is people say, order doesn't matter when you're writing out a set. Okay? All right, now, when you have a set that only has finitely many elements, then it's very easy to just write them out. Well, I shouldn't say very easy. What if there's 1,000,000 elements? Then it would not be easy to write it out. But in theory, you could, right? And you would call that a finite set if there's finitely many elements. Okay? Let me introduce a word for you here. Definition. The cardinality of a set is a measure of how many elements are in the set. Okay? Look at how I wrote that. I didn't just say the cardinality of a set is how many elements are in the set. I said it is a measure of how many elements. And that's because if there's finitely many elements, then it's really easy. You just count them and see how many there are, and that's the cardinality of the set. Okay? But if there's infinitely many elements, then it gets quite tricky, and we'll deal with that later on. Okay? So, here's what we're going to use for cardinality is vertical bars. So I'm going to write this here. Vertical bars with the A in there. That looks like absolute value of A, right? But here's how I know it's not absolute value. Because A is not a number. Absolute value is something that you put around a number. Okay? Since A is not a number, then that must not mean absolute value. What is A? It's a set. So I know that those bars mean cardinality. Okay? And in this case here, the cardinality of A is 5 because there's 5 elements in A. Okay? You can certainly have a set with nothing in it. Let's do this definition. I mean, why not? Why does a set have to have something in it? Can't I have a cardboard box with nothing in it? And if a set is just like a cardboard box with, you see what's in there to see the elements. If I look in the box and it's empty, then I have an empty box, right? There's nothing wrong with that. So it's the same way with sets. A set, well, actually, I should say the set with no elements is called, well, let me ask you, what would you call a box with nothing in it? You would call it empty, wouldn't you? An empty box. So the set with no elements is called the empty set. Okay, here's what it looks like. That's what it looks like. That's the empty set. It's a set. You see the curly brackets. That means it's a set. What's in the curly brackets? Nothing. They're empty. So it is an empty set. Okay? Now there's a symbol for empty set, just like there's a symbol for pi. That is a circle with a line through it. Or, I mean, I'm not going to object if you draw a 0 with a line through it. That's also considered a correct symbol for the empty set. I just don't like it as much. I like the circle with the line through it. We don't need to get into why that is, okay? It's just personal preference. All right, let's see here. What else? I'm going to shrink this down so we can see everything at once here. Okay, so we have set and element. Notice I didn't write definition on that first sentence. That's because those are usually considered undefined terms, kind of like in geometry, the words point and line are considered undefined terms, right? So in set theory, the words set and element are considered undefined. They're just common notions that we agree upon the meaning, but we don't actually say definition, okay? All right, and then we defined cardinality, we defined empty set. Okay, let's define some of the major sets that you've seen before in your mathematical journey. Okay, so we have, let's label this some important sets. Okay, so you have the natural numbers. And the natural numbers are whole numbers starting with 1. I'll just put an ellipsis there at the end. Okay, so that's the natural numbers. Then you have the integers, which is the natural numbers along with 0, along with the opposites of all the natural numbers. So that would look like this. I'll write in order here, even though I told you order doesn't matter, but it's still nice. So I'll write it like this. The opposite of 5, the opposite of 4, the opposite of 3, the opposite of 2, the opposite of 1, 0, 1, 2, 3, 4, 5, and so on. Those are called the integers, okay? And it's common to use what's called blackboard bold letters for these sets. The natural numbers is usually written with a capital N like this, is how most people write it. In books, you know, I don't really know exactly why this is, but in books, the double stroke is usually on the diagonal line. So in books, it's always typed like that here. But when people write it by hand, they almost always write it that way. Okay, so that's natural numbers. The integers is called with a capital Z, and that's just because the German word for integers starts with a Z. So that's how you write integers. Okay, so these are natural numbers, and these are integers. And I'll just point out for you that the set of natural numbers is also the set of positive integers. Notice that? Okay, now, those sets are infinite, right? There's infinitely many elements. So number one, if I asked you for the cardinality of that, well, again, we would have to talk about that in more detail, and we'll get to that later. So let's not worry about it right now, okay? Now, even though there's infinitely many of those, it's still easy for me to indicate the sets, right? By just using the ellipsis. You know what that is, ellipsis? It's those 3 dots. Even though I'm not writing out every number, and in fact, I couldn't write them all out. It would take me longer than my lifetime. But it's still easy for me to indicate what the sets look like, okay? Now, let's go a little bit further. What about rational numbers? Okay, well, let me go ahead and first tell you the letter for that. The letter's a Q. Again, we can thank the Germans for that. And people usually write their blackboard Qs, blackboard bold Q like that. Okay, this is the rational numbers. I'm sure you know what rational numbers are. They're fractions, right? Or more specifically, we say they are numbers that can be written as a ratio of integers. So, how many are there? There's infinitely many, correct? But I would have a hard time indicating all of them, right? Like if I wanted to do this with an ellipsis, like I did with the natural numbers and the integers, how would I do that? I mean, I suppose I could say a half, a third, a fourth, and so on, right? Whoops, what happened there? But that's not going to be good enough, is it? Because even I do that, I still have not even scraped to the top of the iceberg, right? There's so many more rational numbers than there are integers. Or are there? Well, I don't know. We're going to have to discuss that later in the semester. But I can definitely tell you that I'm having a hard time figuring out a way to write down all of the rational numbers in there, or to write down, something that would indicate all of them. So I'm going to show you a new trick. When there's just too many things to write down in a set, we use what's called set builder notation. Okay, and I think the best way to do this is for me to just write it and then point out the different parts for you. Okay, so here's what I would write. There's a couple of ways of writing it. Okay, I'm going to write it my way, and then I'll also write it the way that it is in the book. So here's what I would write for rational numbers. What do they all look like? They all look like integer over integer, right? Except the bottom integer can't be 0. So I can write this, m over n. Okay? And then I'm going to put a colon here. Nice big colon. Okay? And then I'm going to say m comma n, this fancy little symbol that looks kind of like an E, integers. Oh, and also that n can't be 0, right? Okay, let's look at that. What do you think this thing means? It looks like an E, doesn't it? Have we defined any words so far that start with an E? Oh, there's one right there, elements. Well, guess what? That symbol is the symbol for is, or in this case are, since it's plural, there's two numbers there, are elements of. Okay? I should go up, I'm going to scroll up there, and we're going to write that down next to the definition of element. Okay, I'm going to write X, and then this thing. It also looks kind of like an epsilon, doesn't it? But it's technically not an epsilon. Okay, so that means X is an element of the set A. Okay, so let's go back down to where I wrote this and let's dissect what I wrote. So let me read this for you. I'm going to highlight as I go from left to right, and I'll say the words that go along with the symbols. Okay, so it says Q equals the set of m over n such that, that's what that colon stands for, such that m and n are elements of the integers. And then the rest is easy. And n does not equal 0. Okay, so I'm going to say it again all at once now. Q equals the set of m over n such that m and n are elements of the integers and n is not 0. Okay? Now, that colon, that means such that. I find a lot of students, oh, I accidentally erased our Q. I find a lot of students don't like that colon and prefer instead a vertical bar. You can do either one right here. Either a colon or a vertical bar. But either way, it stands for the phrase such that. Only in this is called, I should write this down. When you do this kind of notation here, this is called set builder notation. And when you're doing set builder notation, that vertical bar or colon, whichever you prefer, stands for the phrase such that. But it's the only time that a vertical bar or a colon means such that. Outside of set builder notation, you do not use a vertical bar or a colon for the phrase such that. Okay? Now, in the book, it's written slightly differently. I personally think it is a bit overkill, but this is how it is in the book. I'll just show you. It says, the set of all x such that x equals m over n, where m and n are integers and n is not 0. So look at what I wrote in gray and what I had previously wrote in black. I hope you can agree that that says the same thing. I think the way it's written in black is more efficient and more concise. Okay, but if you like the way it is in gray better, that's fine. Okay, I'm going to erase it for now. So you see, let's summarize. An empty set is called the empty set, and that's how you write it, either the circle with the line through it there, or literally a set with nothing in it. Okay, a finite set is easy to write because you can just list the elements out and put the brackets around them. Okay, or you can give it a name. Infinite sets tend to be harder to write because there's infinitely many things, but if it's not too complicated, you can use an ellipsis, or in the case of the integers, I needed 2 ellipses, or ellipsi, I don't know. Okay, and then if it gets more complicated than that, then you can try set builder notation. Okay, now here's another one. What about the set of real numbers? So that one we call with a blackboard bold R. And I'm not even going to bother trying to write that in set builder notation. Okay, it's just, I mean, what would I write? The only thing I could think of would be to write it's the set of all x such that x is a real number. But clearly that's not going to suffice, because then I'm just using, it's circular, right? I'm just using the real numbers to define the real numbers. So real numbers is really, it's really almost like an undefined term itself, just like the word set. Okay, it's just a common notion that we kind of have to agree on. You can define the real numbers and give it an actual definition. And if you take real analysis, you'll probably do that. But for right now, we're just going to take it as an understood concept. Okay. All right. There's also complex numbers, by the way, and we're not going to worry about that right now, but here's the symbol for complex numbers. But I'm going to erase that. I don't want to leave that on the screen. Okay. Let me think of where we are and what we still need to cover. Well, what about intervals? We should talk about intervals. You've used those a lot in previous classes. So let's scroll up here, okay. And let's write intervals. Okay. So, what kinds of intervals have you seen in previous math classes? You've seen ones like this. That's what we call a closed interval, right? And you've seen ones like this, which is called open. And you've seen intervals that look like this, and ones that look like this. Those are all finite intervals, okay? A closed interval, an open interval, and then 2 that are neither, okay? But they're all 4 finite. And then what about infinite intervals? You can have something like this, and something like this. You can have something like this, or this, right? And I can think of one more, and this one's not listed in the book, which is kind of surprising because it's very simple, and that's this interval. Okay, so let's write down all of those in set builder notation in order to give them an actual definition. Okay, so the first one, what we call the closed interval from A to B. What is that? If I asked you, what is that? You would probably say all the numbers between A and B, including A and B, right? But how about, let's write that using mathematical language and symbols, okay? So here's how I would write that first one. I would write that thing equals the set of all x's in the real numbers such that x is equal to or greater than A and less than or equal to B. See, I'm using set builder notation to give an actual definition for the closed interval from A to B. Okay? And then for the open interval, it would look the same, except without the equals. So I would say the set of all x in the real numbers such that x is greater than A and less than B. Okay? The next one would be the set of all x in the real numbers such that x is equal to or greater than A and less than B. So go ahead and think about how you would write the remaining, well, let's leave the last one by itself for now. Let's just say the next 5. How would you write those? Oh, and I see I accidentally repeated myself down there where I meant to put a parenthesis. Okay, so take a minute and write, or at least just imagine in your head, how would you write the next 5 intervals with set builder notation? I'm going to pause for a second and then I'm going to just write them all out. And then you can think about what you wrote or what you pictured in your head. See if you agree with the way I'm writing them. Okay. All right, now what about the last one? Well, the last one's very, very different, isn't it? The last one is actually the set of all real numbers. Okay, so now you have actual definition for these intervals. All right. We're just about done. Let's see where we are on time. It's been 35 minutes. I think we're going to stop here, okay? Some of the lectures will be longer. Many of them will be longer, let me say. But this is just the first lecture, and I just want you to get comfortable with the symbols and the words involved in writing sets and elements, and especially set builder notation. Okay, and we will continue from here in the next lecture. Okay, lecture 2, we're going to talk more about finite cardinalities. What did I say last time does cardinality mean? I said it's a measurement of how many items are in the set, right? I should say elements, not items. How many elements are in the set, right? So you might say you just count how many things are in the set, and that's the cardinality. And that is completely true unless there's infinitely many things in the set. Then it gets a little bit more complicated. And we're going to ignore that complication today. We're only doing finite cardinalities, okay? So that means you can look at the set and simply count how many things are there, and that would be the cardinality of the set. Okay, so let me do this. We'll just start off really simple. Let's look at that set. Okay, and I want to know the cardinality of that. Remember, the symbol we're going to use for cardinality is identical to the absolute value symbols. So I could do that. And what would be the answer? How many things are in that set? I see 5. So that's the answer. Okay. Another way to do it, just so that you know, is I could have given that set a name and said A equals that, and then I could have written the cardinality of A equals 5. Okay? All right, let's go back to the way it was. Now, it's a pretty simple concept, I think, right? Do you agree? But there are some small technicalities that are very, very common for confusing people at first. It's very easy to get past this confusion, and then it will probably never confuse you again, okay? But probably the first time it will. And all we need to do is just point out the possible confusion and get you past it once, and then it'll be fine. Okay? Look at this. I'm going to take a set. Okay? And inside of that set, I'm going to put a set that has, let's say, the numbers 1/2. My pen's not working. What's going on here? Give me 1 second. There, that fixed it. Okay, let's say 1/2 and 5 and pi. How about that? So I have a set, and inside that set is another set that has 3 elements. So I ask you this question. What is the cardinality of that? Think about it for a second, okay? And I'm going to tell you the answer, and you either got it right or you got it wrong, and it's one of these two answers. I know it. And the answer is 1. Okay? Some of you said 3, and that's perfectly fine to say that, but it's not correct. The answer is 1. Okay, let me show you the reason why. I'm going to draw a picture here. Remember the analogy I said in the last lecture, because this analogy will help you on almost every single problem about cardinalities, okay? And that is, what is a set and what are elements? Think of a set as a cardboard box, and the elements are the things that you see when you look into the box, okay? Listen very carefully what I said. I didn't say the elements are the things in the box, although that would be true, but that's not the way I said it, is it? I said the elements are the things that you see when you look into the box. Okay, so let's look at the first problem. This set right here. Okay, so what is that? It's a cardboard box. Okay, and inside that cardboard box are 5 blocks, like the kind you probably had when you were a kid. One of them's got the number 5 on it. Here, to save time, this is going to take us all day, so to save time, I'm just going to draw a square, okay? That's a little block with a 5 on it. And there's a block in there with a 3 on it. And there's a 7 and an 8 and a 9. Okay, so when I open that box and I look inside, how many things do I see when I look down in that box? I see 5 things, right? And that's why the cardinality was 5. Okay? So that one is not ever cause anybody any confusion, for the most part. Okay, now let's do the next one. And let's see why that answer is 1. So what I have here is I have a big cardboard box. Okay, there's a big cardboard box. And I'm asking, how many things do you see in that box? Okay, so what's in that box? In that box is a cardboard box. Let me erase these dash lines. I think we're going to have too many lines in the picture. Oh, I don't want to go that far. Hang on. Okay, there we go. Okay, inside that box is another cardboard box. You see how I'm making these boxes closed? I'm doing that on purpose. It's like they're taped closed, okay? And inside that little box are 3 numbers. There's a block with a 1/2, and a block with a 5, and a block with a pi. Okay, now I open the big box. And I look to see, how many things do I see? There it is again. Remember, I'm not saying how many things are in there. I'm saying how many things do you see? So look at that picture. If you look down in that box, how many things would you see? Now, mind you, this is made out of cardboard, not plexiglass. You can't see through the cardboard. So when you look inside that big box, what are you going to see? You're going to see a cardboard box that's closed. I drew it that way on purpose. Right? Are you going to see the 1/2 and the 5 and the pi? No, because they're inside of another box and you can't see through that. You're not Superman or Wonder Woman. Okay? So how many things do you see when you look in there? You see 1. And so the cardinality of that set is 1, because that's how many things you see when you look in there. Okay? Now, the cardinality of this set that's inside of the other set, okay, the set inside has a cardinality of 3, because if you opened that little box and looked inside, you would see 3 things. So the cardinality of the little set is 3, and then that little set is inside of the bigger set, and that little set is the only thing in the big set. So the cardinality of the big set is 1. Okay? I hope that makes sense. If it doesn't, you can ask me during one of the discussions. But usually the box analogy is something that will help you through any difficulty of cardinality, as long as there's not infinitely many elements. Okay? All right. Let me erase that picture. So let's just do a few more now. What if I did something like this? Here's a set that has inside of it the number 10 and a flower. And a set containing the numbers 1 and 2, and that's all. What is the cardinality of that set? You have it? The answer is 3. I would see 3 things when I peer down into that box. I would see a number 10, I would see a flower, and I would see another box. Here's the other box right there. Well, here, let me do it like this. So there's the number 10 that I would see, and I would see a flower, and I would see another box. So I see 3 things. I don't see the 1 and the 2 when I look inside the big set, because the 1 and the 2 are inside of something else. Okay? It's not that hard, right? It's pretty straightforward. All right. Let's talk about the empty set. Do you remember what that is? It's exactly what the name says. It's an empty set. What's the cardinality of that? That's not a trick question. It's 0. The cardinality of the empty set is 0 because you don't see anything in it. Because there is nothing in it. Okay? But don't get that confused with this. Oh, I see I erased that too from that earlier problem. There we go. Don't get that confused with this. Here's a problem that we like to ask that is always confuses people the very first time. But then again, as soon as you see, oh, I understand now the mistake, then it'll never bother you again. Okay? So because I scrolled off of the screen, I'm going to just write again here. This is what the empty set is. And the cardinality is 0. Okay? Now, look at this set. Is there anything in that set? And if so, or if not, what's the cardinality of that set? Think about it. Now again, there's only 2 answers that anybody ever says for this. And one of them's right and the other one's wrong. Okay? Here's the correct answer. Up here, let me write the cardinality of the empty set for you. The cardinality of the empty set is 0. Okay? The cardinality of this set is 1. Because there's something in there. You know what's in that set? The empty set is in that set. It wouldn't make sense, would it, if I did this? I'm going to take an empty box. That's the empty set. There's nothing in there. That's the empty set, and its cardinality is 0. Okay, and that's why we get that up there. Okay, but now, what does this say? This says, it doesn't say the empty set, that's what's important. It says a set with the empty set inside of it. So, my claim is that that set's not empty. So let's take that empty box that I drew down there, and now I'm going to put that empty box inside of a bigger box. And tape it shut. Okay, and then I'm going to ask you to open that box and see if there's anything in it. So let's open that box. Okay, and let's say you look inside. Is there anything in there? You see, if you said, no, this big box is empty, then I would say, oh, you better go to your optometrist. Because when I look in that box, I very clearly see that there's something in there, isn't there? This box is inside there. So you can't say that the cardinality of this set is 0 because that set's not empty. The cardinality of this set is 0. That's the empty set. Okay? But this set is not the empty set. That set has one thing inside of it. So the cardinality of that set is 1. Okay, you see how that works? It's not confusing, it's just that almost everybody will say the wrong answer first, but then as soon as they realize, then they got it straight. It's not the sort of thing that keeps causing problems over and over again. Okay, let's do one just a final practice on this. Let me write a set that has inside of it, let's say 1, and the set containing 2 and 3, and the set containing 4, and the set containing 5, and the empty set inside of there. Okay? So I'm going to ask you several questions about this. Okay? There's a set right there, the empty set. What's the cardinality of that? It's 0, right? Cardinality of the empty set is 0. Okay? Now, let me ask you a new question. Here's another set. What's the cardinality of that? Okay, I hope you say it's 2 because that's correct. That set has a 5 and the empty set, or the elements. Okay? So that cardinality is 2. Now, here's a bigger set. What's the cardinality of that? Careful. Don't be too quick to answer. Look at it carefully. You know how many things I see in there? I see a 4, that's one thing. And I also see this set. I see 2 things in there. Not 3, just 2. Because when I look in this set that I've underlined in red here, when I look in that, I don't see that 5 and that empty set because they're inside of a smaller box. I can't see through the cardboard of that smaller box. Okay, do you see what I'm saying? All right, let's move over. Here's another set here. That one's a little bit easier. What's the cardinality of that? That's 2. Is that a set? No, that's not a set, is it? There's no curly brackets. All right, now, final question, and this is the big one. What's the cardinality of that set here? Well, let's see. How many things do we see? Let's count them. I'll circle them in purple. There's one thing that I see. Here's another. And here's another. How many things do I see? I see 3. The cardinality is 3. By the way, you might notice this. Look. You can also use the commas to help you count that. There's 2 commas, so that means how many things are being separated? 3 things. And why would I not count this comma? Because that belongs to these brackets. You see? So that's not a comma for the big set, that's a comma for that smaller set. You see what I'm saying? Same thing here. I wouldn't count this comma because it belongs inside of these brackets, so that's for that smaller set. And I wouldn't count this comma because that is for this set. The only commas for the big set are the ones I circled in red. And there's 2 of them. 2 commas means 3 elements. Okay? All right, now I just want to do a little bit of practice with set builder notation. We went over that in lecture 1. What if I wrote this? The set of all x in the integers such that x squared is between 10 and 100. And the question I want to ask is, What's the cardinality of that set? Okay, so I'll give you some advice. How about if we just rewrite that set by listing the elements? Because I don't think there's going to be all that many. So that set would really just be what? Let's see. 2 squared is 4, so that's not going to be in there. 3 squared is 9, so that's not going to be in there. 4 squared is 16, that'll be in there. 5 squared is 25, that's between 10 and 100. What else will be in there? 6 will be in there, because 6 squared is 36. 7 and 8 and 9 will be in there. But 10 won't be there because 10 squared is not less than 100. So that's the whole set right there, and we are being asked for the cardinality of that set. So it's actually a very easy question when you write it that way. And the answer is 6, isn't it? Okay? So that's cardinality for finite sets. It's a counting problem. There's not a lot of really advanced mathematics involved here. It's just a matter of understanding how to count things that you see inside of a box, and especially just getting over that hurdle of sets inside of sets and how that is treated when you're trying to find the cardinality. Okay, so that's all for today. It's a short lecture today. Okay, and next time we're going to move on and we're going to do something called the Cartesian product. Sounds a little bit more technical, but it's not going to be that hard, I don't think. You actually, to be honest with you, you are very, very familiar with Cartesian product already. You just have possibly not been used to using that name, but you actually already know what it means. All right, and that's for next time. So if you have any questions about this, come to the Zoom discussion and ask the question, and I'll be happy to help you through it again.